All right, ready to dive into some C. Today we're all about C memory management, breaking down this lecture script about how C organizes data and why that even matters to, well, someone writing code.
It's almost like thinking of memory like a city. You've got different zones, right? For different purposes, each with, their own quirks and rules. Get these zones and you get efficient, bug-free C.
I like where this is going. Okay, so the script starts off with static and dynamic memory. Is it safe to say static memory is that meticulously planned city center? Like everything's in its place?
Yeah, exactly.
Yeah.
Those historic districts, maybe, with the big old buildings, that's your static memory. Allocated when the program starts, stays put. And within that, you've got the text or code segment houses the actual program instructions.
Unchanging, right. Like those are the city blueprints, can't be messing with them mid-construction.
Spot on, changing those on the fly. Recipe for disaster. Then we've got the initialized data segment. That's where global and static variables live, the ones with, predefined value.
So if I declare a global variable, give it an initial value, that's where it goes. Like we've assigned it a building in our well-planned city center. What about variables without a starting value? Where do they hang out?
Uninitialized data segment. Think of it like reserving those plots of land, for future construction. But here's the thing. Even if we don't give them specific values in our code, C initializes them to 0 at the start. It's like laying down some basic infrastructure before the real building starts.
Candy. All right, so that's our static memory organized, predictable. But what about those times you need more flexibility? Like you don't know how much memory you'll need until the program's running. That's dynamic memory territory. Yeah.
Yeah, you got it. Think of it as, the city outskirts, maybe. Things are a bit more free-flowing. You can buy land, build what you need, even demolish and rebuild as your needs change.
Ooh, exciting, but also kind of intimidating. The script mentions the stack and the heap here, like they're the key players in this dynamic landscape.
Absolutely. The stack that's like the bustling commercial district of our memory city. Super efficient, handles all those short-term transactions, your local variables, function calls, all happening lightning fast.
Okay, so how does this stack actually work? The name makes me think of, I don't know, like a wobbly tower of Stark.
Not a bad analogy, actually. It's last in, first out, LIFO. Picture a stack of plates, right? You can only add or remove from the top. Might seem limiting, but that's what makes it so efficient. Each function call is like adding a plate, creating this stack frame, holding its local variables, parameters, return address, the works.
So each function gets its own little workspace on top of the stack.
Yeah.
And when it's done, it's like, boom, clear that workspace, plate's gone, move on to the next one.
Exactly. This neat system keeps everything isolated, no data mix-ups. But like any stack of plates, there's a limit to how high you can go.
Cue the dreaded stack overflow.
Yeah.
You pile on one too many plates, the whole thing collapses.
Precisely. In code, that usually means too many nested function calls. Or you're trying to stuff massive data structures onto the stack, like trying to fit a skyscraper on a postage stamp in our city. Not going to happen.
Makes perfect sense. Okay, so we've done the organized streets of the stack, but what about the heap? Sounds like we're venturing into a whole different neighborhood.
Oh, yeah. The heap is more like the city's outskirts, right? Vast, flexible, ripe for development. This is where you, the programmer, get to be the master builder.
Sounds exciting. Tell me more about this land of opportunity for a C programmer. So we're in the heap now, outskirts of our memory city, right? Where all the big data structures and crazy projects go. A bit more freedom than the stack's strict zoning laws.
It is, yeah. Think of it this way. On the stack, you're basically getting a pre-allocated apartment. Efficient, but you can't rearrange the walls. The heap, now that's like buying raw land. You decide what to build, how big, and can even knock things down and rebuild if you need to.
Okay, I see why understanding this is so crucial. It's where you get to really, I don't know, exercise those C programming muscles, right? But like greater power, greater responsibility and all that. The script's making it clear that managing memory in the heap is all LL on us.
100%. No more automatic allocation and deallocation like we had on the stack. Here, we're requesting memory when we need it, and this is crucial, releasing it when we're done. We're talking full-on construction and demolition crews here. Got to be careful not to leave a bunch of abandoned buildings lying around.
Right, the infamous memory leaks. So if you get messy in the heap, you basically end up with a ghost town on your hands. Does that mean the program just grinds to a halt?
Might not be that dramatic, but definitely bad news. Every leak, it's hogging up space that other parts of your program might desperately need. Over time, your program's a memory hog, slowing the whole system down. Worst case, crash because it can't get what it needs from the operating system.
Ouch, yeah. Cleaning up after yourself is important. Okay, so the script mentions these functions. Malloc, calloc, realloc are tools for like responsible development in this heap zone.
Those are your bread and butter.
Yeah.
Malloc, that's how you claim your chunk of memory. Say you need to store a massive array of numbers, call malloc, tell it how many bytes you want, boom, reserve space, just like buying a plot of land.
Gotcha. If Malloc is buying the land, what's calloc for? It's like Malloc, but with a bit more, I don't know, organization.
Sharp eye? Calloc does a little extra, it allocates the memory, yeah, but it also sets all those bytes to 0. Clean slate, no leftover data from whoever was there before. Useful stuff.
So like getting the land cleared and prepped before we bring in the construction crew. Nice. And then there's realloc. Is that for when our grand plans for the skyscraper went bust, or we decided we needed 2 skyscrapers?
You got it. Let's say your program needs more breathing room than that initial malloc provided. Don't start from scratch. Realloc lets you expand that memory block. Need less. Shrink it down. It's like getting a contractor to add an extension or maybe demolish a wing as your needs change.
Wow. Okay, so memory management in the heap, it's all about careful planning, isn't it? Thinking ahead. Any tools or like best practices to help us avoid those memory leak disasters and those dangling pointers the script warned about?
Oh, absolutely. One common one is RAII, stands for resource acquisition, is initialization. Sounds fancy, but it basically means you're tying the lifespan of your memory to objects in your code. Objects gone, memory is released automatically, no leaks.
That's pretty slick, like having a built-in demolition crew that swings into action when a building is marked as abandoned. But you mentioned dangling pointers. Those sound like trouble.
They can be. Remember our signpost analogy. Say you have a pointer at your signpost pointing to some data on the heap. We demolish that data building's gone, but the pointer, that signpost, it's still there pointing to nothing.
And if you try to follow that signpost expecting a building, total disaster.
You'd fall right into the foundation, right where that building used to be. Accessing memory through a dangling pointer. Unpredictable. Clashes. Corrupted data. Might even keep running, but with the wrong information. That's a nasty one.
This is making me realize just how much can go wrong in the heap. Feels like mastering C memory management is as much about avoiding disaster as it is about writing beautiful code.
You're getting it. The heap gives you incredible power, flexibility, but it demands respect. Understand those concepts, good practices, and you're on your way to building really robust C programs.
We've done the stack, we've done the heap,
Yeah.
explored these crucial players in C memory management. Stack for those quick transactions, efficient as heck, and then the heap, where you get to be the master planner, right?
But what about pointers? Feels like they're lurking around every corner in this C world. You're not wrong about that. Can't talk memory management in C without really getting into pointers. They're the bridges connecting your code to the actual data, wherever it's stored.
All right, lead the way. I'm ready to unravel these pointers. Pointers, pointers, pointers. They're like the addresses for specific spots in our memory city, right? But the script also says they're variables that store memory addresses. That seems a bit more complicated than just like an address on a letter.
Yeah, good point. Pointers are variables, meaning they take up space, right? But instead of holding a number or a letter or whatever, they hold the address of where other data lives. Like, instead of writing down your friend's whole apartment layout, you just jot down their street address. Tells you where to find all their stuff.
Okay, that clicks. So in action, how do these pointers work? There's this word dereferencing that sounds kind of intimidating.
Not so bad, actually. Let's say you've got a pointer called, we'll say PTR, pointing to an integer variable, call it num. To get the actual value inside num to dereference that pointer, we use the asterisk, the in front of it.
So print PPR would give us the value of num using our pointer.
You got it. It's like saying, hey, not the address in PTR, but the value at that address.
Gotcha. But why even go through that? Why not just work with the variables directly? Seems like extra steps.
Great question. One word. Efficiency. Especially with larger data. Say we want a function to modify the original data, not a copy. Or we've got this massive data structure, don't want to waste time in memory copying it over. Pointers let us pass by reference.
Ah, right. Like we talked about that earlier with copies. It's like sending blueprints instead of the actual building plans.
Exactly. Pointers. We're handing over the actual plans, direct access, way more efficient.
So we get more elegant code, especially for those complex data tasks.
Precisely. It's like giving those functions the power to directly remodel our city, not just suggest changes on a copy of the blueprints.
Powerful stuff. But, like we've seen, powerful tools, potential for chaos, any pointer-related traps we should be wary of.
Oh, yeah. One of the worst is the dreaded segmentation fault. That's when you try to access memory. You shouldn't be anywhere near, like your pointer's got an invalid address.
Following a signpost to a non-existent building.
And walking right off the edge of the map, it's the OS going, nope, not happening. Tough to debug those because they cause crashes in the weirdest spots.
Sounds like working with pointers, you need a solid grasp on how C does its memory thing, plus a healthy dose of caution.
100%. But mastering pointers, it's like unlocking a whole new level of C. You get this incredible control over memory, write crazy efficient code. Like they're handing you the keys to the city, right? But use them responsibly.
Love it. So for anyone out there just getting started with C pointers, they're your friends, but powerful friends. Treat them with respect.
Well put. Understand the stuff we talked about. Use those pointers safely, effectively. You'll be writing solid, efficient C-men in no time.
This deep dive has been awesome. Stack, heap, pointers, we covered it all.
It's been a pleasure. Remember, C, memory management, it's a journey, right? Experiment, make those mistakes, keep learning. Writing efficient, powerful code. That's the reward.
And on that note, I think we'll wrap up this deep dive into the world of C memory management. Until next time, everyone, happy coding.